So for this very last section, our very last video we're ever going to do together, we're just going to take a few minutes, a little bit of time to talk about some assumptions that we are making, whether we realize it or not, and then common violations of those assumptions. So the biggest one is nonlinearity. So when we use least squares regression or multiple least squares regression, we are assuming that the data is linear, at least within the area that we're looking at. It may not be linear within from 0 to infinity, but if you think back to the data that we've been working with the debt and income level, we weren't looking at income from 0 to $1 billion, right? We were looking at income from about 50,000 to just a little over 100,000. So within that, what we call the relevant range, the data is linear, then we can use least squares regression. But if it's not linear, then we can't use least squares regression. There are other methods that we can use called non-parametric statistics, which are beyond the scope of this course, but you could take on in your master's program or in higher level statistics classes that you are appropriate to use when the data is not linear. So the easiest way to check if the data is linear is just simply to graph it. So here we're looking at what's called a residual plot, and I'm going to show you in Excel in just a minute how to graph that. It's an easy way to check for linearity. And we can see that in this particular data that the data is not linear. It's a U-shaped, it's a parabola. And so we could not use least squares regression with this. So let's jump over to Excel and look at this in real time with some real data. So here we are back in our chapter 12 Excel workbook, and I'm on the happiness_age Excel spreadsheet. So this is a study that's testing whether your age has an effect on your happiness. Now obviously this is one of those that can only go one way. Obviously your happiness doesn't determine your age unless they were asking maybe what age you feel like, but that's not what was tested here. So they took the person's real age and then they asked them on a scale of 0 to 100, how happy are you? And we're given the data here. Now there's two ways that we could graph this. First of all, we could just very simply use a scatter graph. So in order to use a scatter graph, remember that our X variable, our independent variable, has to be listed first, and our dependent variable Y has to be listed second. So in this case, age is the independent variable and happiness is the dependent variable. So before I could do just a plain scatter graph, I would want to move this data around so that I have age listed first and then happiness. And so I can just highlight all of that data, insert my scatter graph, and here we can see, and again we know that we can adjust the graph, but we can clearly see that this is not a straight line. So we could not use linear regression on this. Now let's just delete this chart. And another thing that we could do, we could go ahead and let's just for fun run the regression analysis on this. So let's choose regression here. And remember, this is put in a little bit, it's backwards to how we did it before. So my Y variable is my happiness. And my X variable is my age. And I do have labels, and I want my output range to be here, and let's just put it in E1. But now I want to go down here and notice that I can click on residual plots. I can also click on line fit plots. Let's just go ahead and click on that one as well. Click OK. So here I get all of my summary statistics. I get my age and my intercept, and my age and my y-intercept. I get my t-stats and my f-stats and all of that kind of good stuff. I get my r-square and my adjusted r-square. Notice that my r-square is relatively low, right? It's only 32%, saying that at least age isn't the only thing predicting happiness. I do get p-values, notice, that are for age is significant, statistically significant, at even at the 99% confidence level with a 1% significance level. I have a p-value for age that is statistically significant. However, we know that we can't rely on this because we already know that this is nonlinear data. So really none of this makes sense. So again, here's a couple of things that we plotted here. Here we've got our age residual plot. Now notice this is plotting it around 0, but we can still see, for example, that this is a U-shaped data set. It is not linear. So this is our clue that, hey, we can't use this. Also, if we look at our age fit plot, and I'm going to, make that bigger, we can see this is kind of gives us an example of kind of like that scatter plot with the trend line. We can see, for example, that the trend line fits through there, but the data, again, is not linear. So this is least squares regression is not an appropriate model to test this data. Now, again, as we've said before, you would need to use a different statistical method, one that we're not going to cover in this particular course, but you can take non-parametric statistics, and that would help you with how to analyze that particular data set. So another common assumption is what we call multicollinearity. So multicollinearity results when you have two or more variables that have a linear relationship with each other. So in other words, there's a large degree of overlap, and it's not necessarily overlap in data, but it's overlap in how the data reacts. So an example would be if you're looking at let's say that we're a car dealership and we're looking at how successful particular car salespeople are. We might look at one piece of data as number of cars sold, and then another piece of data we might want to say, well, what's the number of customer survey satisfaction surveys that get returned? After you buy a new car, they always want to call you or email you or something and ask you to take a satisfaction survey. So we might say just the act of filling out that survey might tell us whether you were happy or not happy with your service, because typically we find that people only fill out these satisfaction surveys if they're really, really happy with their service or really, really not happy. But obviously the person who sells more cars is probably going to have more people who fill out that satisfaction survey. So there may be a high degree of collinearity there between that. So that would skew our results. Now, one way that we may detect multicollinearity, because there's not really a good just test for it, is if your R squared is very high, but each of the individual variables, the coefficients, are relatively low or insignificant, okay? So maybe they have high p-values. So that's kind of a clue that there's some collinearity there. Also, if you have, again, multicollinearity is if you have a correlation coefficient between two x variables that's either very high or very, very low. Another one that's important to look at is, for example, if the wrong signs on the coefficients seem to exist. So a wrong sign, or a sign that's not what you expected, you were expecting a positive relationship, but you got a negative relationship, doesn't always indicate multicollinearity. It could just be that the data was not as you predicted, but it could, again, indicate that there is some high collinearity there. For example, if we go back to our example with the car data, if you are with if we were talking about our data with a car, typically we would expect the value of the car purchased to have a positive relationship with the income of the purchaser, meaning the more money you make, the more expensive of a car you're going to buy. But if we saw that, hey, for example, let's say that income was negatively related with car the price of the car, well, then that means that the less money you make, the more expensive a car you buy. That doesn't really make sense. So if it just doesn't make sense, we need to question. We wouldn't automatically determine that there's not collinearity. I mean, certainly I do have known some people who bought cars that they couldn't afford. Maybe it was an image thing, so we can't just automatically assume, but it's something to make us question. We want to then go back and maybe look at this a little bit more and determine if there's some collinearity there that is messing with our results. So a good remedy might be to drop one of the collinear variables, one of the variables that is causing redundancy. So collinear variables mean that you have two variables that are essentially measuring the same thing or really similar things. So we might want to try to drop one of those that's measuring the same thing, or if we really suspect that, hey, there's really not collinearity here, even though it looks like it, then maybe we need a larger sample size. And so with a larger sample size, we might find that those two items aren't necessarily related, but they were in our sample that we drew. Now, another one is changing variability. So again, this is when we're assuming that the variability remains the same across all values, maybe even across time. And so if it happens that the variability changes, then we can't trust the test. So another way, or the best way to look at that is to, again, check that graph. So if we see that there is no discernible pattern across that graph that we looked at, then that means that this is not an issue. But if we're detecting a pattern, then there is. So here we're looking at some data. This is about convenience stores and their sales and their square footage. So if you notice, so here we have our trend line, essentially, our square footage, that's essentially our y-intercept. But if you notice how the data points kind of come out of here almost in a funnel-like pattern, this is called heteroscedasticity. It's a really hard word to say and spell, but heteroscedasticity means that the variability is not constant over the sample. So if you think about it, really small convenience stores in this example probably just sell very basic necessities. They might have, some sodas, some candy, maybe, cigarettes, that's kind of it. But as we get larger and larger and larger, they sell lots more stuff. If you've ever been in a Buc-ee's, I mean, I'm pretty sure, I don't know that there's pretty much anything you can't buy in a Buc-ee's. So it would make sense that you would see a lot more variability in the sales as we get larger square footages. So in this example, we're detecting, again, that heteroscedasticity. It's kind of a fun word to say after you practice it for a little while. So if we have heteroscedasticity, there are some corrections that we can take. Excel doesn't do those for us, and that is really beyond the scope of this class. But just know that if you look at that residual plot and you notice that heteroscedasticity, you're going to have to, go to someone who's more experienced and wise in statistics than you are, because you can't really rely on those T and F tests now and their associated p-values. So another one, this is very similar to multicollinearity, is what we call correlated observations. So again, this is when there's a high degree of correlation between various observations. This tends to happen with data that is over time, with time series data. And so we may see this kind of pattern happen then. Now, one of the way that you can detect this is if, again, when we plot that data, when we do that plot right there in the regression analysis, notice how there's a pattern here. Again, we're expecting to see no pattern in this residual plot, but here we're seeing kind of a wave-like pattern, especially if we were to graph it further out and we see a wave-like pattern. That tells us that there is high correlation between those observations. And again, this tends to happen over time. If it looks like it's something that's cyclical, what we need to do is, again, correct The data, which Excel does not do for us, and that's a more advanced methodology here, or we need to try to remove one of the observations. So maybe that, and sometimes you can't, sometimes you just have to say, no, I really need both observations. But if we can remove one of the observations that's correlated with another one, then we need to try to remove that. And lastly, if we get our model, but we are leaving out an important variable, then our model's not going to be as good as it should be. So again, there's a tendency to try to put every variable that we can possibly think of in the model, and that's kind of a good starting point. That's kind of what we start with, but then we need to start removing those variables that are not statistically significant, like we did with unemployment. So we would want to remove those that are not significant, and a lot of times you remove them one at a time, because removing one's going to affect all the others, and then we kind of work it down from that until we come up with a good model that has a small standard error, a high R-squared value, so it has high predictive value, and each one of our coefficients is statistically significant. Okay, so we're trying to minimize that error term as much as possible. So again, we've already talked about this, but we want to try to narrow it down to the predictive variables. If we find that we really can't get it down to where our standard error is small, then we need to go back and think, hey, maybe what error is it? What data point is it that I'm leaving out? And sometimes we just have to leave one out because we just can't measure it. It's impossible to measure. And so that just has to be what the standard error term represents. But we want to try to get it as small as we possibly can. So that is the end of our course. I hope that you have learned a lot about statistics, and I hope that I haven't given you just enough tools to be dangerous, because one of the things I hope that you've learned is that statistics in the wrong hands with the wrong analysis can be dangerous. So I want you to be able to try to make good predictions and good analyses, and also have the knowledge to say, I think this may be beyond what I know, and I need to go to someone who has more expertise in this area, because certainly one statistics class is not going to make you an expert in statistics. But what I want you to know is, just because you can run a t-test and just because you necessarily get a p-value less than 0.05 doesn't necessarily mean, as we've looked at here, that that's the right interpretation or that's the right methodology to use. So good luck with your future studies, and it has been a pleasure.